Hello, everybody, and welcome back to introduce uh, a new video and a new application for the plane wall which experiences heat generation. In this episode, we will pass through other applications where there is sort of heat generation in a plane wall, and especially for the one dimensional cases and its application in industry. Thank you for watching and following up this series of videos for this topic. The objectives of the present video is related to the one-dimensional heat conduction where there is a heat generation in the plane wall. Some case studies which are mainly related to the boundary conditions that the wall is exposed to, and we will pass through closure as usual for the videos issued by this channel. Heat conduction equation in Cartesian coordinate where um, energy is generated per unit volume of that domain. The element which has been discussed previously in 3 dimension dx by dy by dz and is exposed to heat transfer in the three directions x, y, and z, and this form of equation has been derived in a previous episode in the form partial square t with respect to x square plus partial square t with respect to y square plus partial square t with respect to x square plus q dot divided by k equal to 1 by alpha partial t with respect to tau. And we said that this equation represents the transient form of heat conduction in a plane wall in the 3 dimension. In this equation, we have alpha as defined before, as which represents the material thermal diffusivity, and the one-dimensional form uh, for a steady state condition has been derived in the form of d squared t by dx squared plus q dot divided by k equal to 0. And if we have a look at the figure, q is perpendicular to the surface and has the direction uh, shown in the red arrow. So the general form which we have derived before, and we called it the magic equation, which is used in the plane wall experience heat conduction and heat generation in the steady state conditions, is represented by equation number 4. Of course, this equation will be repeatedly used through this series of videos uh, for applying different boundary conditions. Now, let us consider the case where we have a constant uh, temperatures at the walls. If we consider the wall, which is shown in this figure, uh, is exposed to heat transfer in one-dimensional form with a heat generation Q dot watt per meter cube with a thickness L, and we want to derive an expression for the temperature distribution through this wall, uh, and we need to find the position of maximum temperature. Solution for this equation. We have the magic equation, which represents by uh, equation 4, and we need two boundary conditions to get the final form of temperature distribution. We have T1 equal to T2, which equal to T, as shown in the figure. Thus, we have a constant temperature on both sides. And such conditions are even available in industry. Uh, for example, a wall is exposed to environment. Then we will have heat transfer to the environment, and the temperature uh, uh, is constant on both sides wherever there is a heat generation per unit volume as a uniform value. Then we have two boundary conditions at x equal to 0 and x equal to L. That is t equal to t of x equal to t. Applying boundary condition 1 in equation 4 uh, and substitute the value of x as 0, then we will get C2 equal to t. And if we apply boundary condition number 2 together with the constant C2 equal to T in equation 4, then that will produce a general form of C1 in terms of Q dot divided by K times L divided by 2 as shown in equation number 9. So if we rearrange and substitute the values of C1 and C2 in equation 4, then we will get the final form P of x equal to Q dot divided by 2K times Lx minus x squared plus T. This is the general form of the equation. How can we verify this form? If we apply, if we substitute the x equal to 0 in equation number 11, then the temperature T as 0 equal to T. And similarly, if we substitute x equal to L in equation 11, then we will get the temperature T at L equal to T. Then equation 11 is correct and right to represent the form of temperature distribution. So the second part of this example, how to find the position of T max. And to get that, we should take the derivative, the first derivative, dt of x by dx equal and equate that to 0. And from that, we will get x equal to L divided by 2. And that means we have the maximum temperature will be positioned at the center. This is because we have constant temperatures on both sides of the wall. Let us consider mathematical example where we have monitored the temperatures through a wall, and we have found for a wall with a thickness of 2 centimeters and experiences a heat generation of 10 to power 4 watt per cubic meter with a thermal conductivity of this material of the wall is 2 watt per meter. Kelvin. One side of the walls is kept at 61 degrees centigrade, and the other side of the wall was exposed to convective thermal fluid with a heat transfer coefficient of 10 watt per meter square Kelvin. The temperature at the exposed wall to convection was measured to be 60 degrees Celsius. Now we need to calculate the temperature at the middle of the wall thickness. Uh, this is another figure representing schematically how the wall can be represented with the boundary conditions, and it is exposed to the fluid. Um, the If we go back to equation 11, which represents the temperature the distribution in a wall experiences um, heat generation per unit volume and uh, non-temperatures on both sides of the wall. If we substitute that according to the boundary conditions at x equal to 0, we have t 0 equal to 61 Celsius, and at x equal to L, then the temperature will be 60 Celsius. Then we have also the thermal conductivity, the thickness of the wall, and the amount of heat generation per unit volume. If we substitute these values in equation number 11, then the final temperature at T of 0.01 equal to 60.75, which represents the temperature at the middle of the wall. Another example for a plane wall, which is disconnected to the previous one, and here we need to calculate the heat flux uh, at the exposed wall to convection and the uh, temperature of the convective fluid of the steady state conditions. Again, the same form, we have the heat generation in the domain equal to heat dissipated to the ambient by convection. This is because we have a steady state conditions. That means the temperature doesn't change with time, but it changes with position. Q dot A times L equal to H times A times delta T. Delta T represents the temperature difference between T wall and T ambient. Then this equation gives T sub A equal to T sub W minus Q dot L divided by HA. H represents the heat transfer coefficient. Then if we substitute these values with TA with T wall, and we have a Q dot, and also we have the other parameters, then TA equal to 40 degree Celsius. And we have a Q dot times A times L, which represents the heat transfer rate, equal to amount which has been represented by the above equation. Then Q divided by A represents the heat flux that is passed at the um, convective part, which is corresponding to 200 watt per meter square. Now, We arrived to the closure of this video. We studied the one-dimensional heat conduction. Of course, that was accompanied by a heat generation per unit volume, the solid wall. We took some worked out examples applied in industry and how we can calculate the temperature distribution of, for example, through a wall. And also we have some references in the description box. You may make advantage of them. And thank you for listening. And your support is required for that. And at the same time, uh, I would like you to subscribe and share this information with others. And thank you. And I will see you in a new episode in the near future. Bye bye.